Hello, everyone. Today we will continue our discussion on phase diagrams of binary systems, but this time we'll focus on partial immiscible and immiscible liquids. At the end of this lecture, the students should be able to first is to discuss the distillation of a mixture of two immiscible liquids. Second is to determine the molar mass of a water immiscible compound through the steam distillation. Third is to construct and interpret a temperature composition diagram for a mixture of two partially miscible liquids. And last is to construct and interpret a temperature composition diagram for a mixture of two immiscible solids that form no reactions, a eutectic reaction forming a congruently melting compound, and a peritectic reaction forming a non-congruently melting compound. Now, let us focus first on partially miscible binary liquids. So consider a mixture of two components A and B. So if they are partially miscible, they have limited solubility in each other at all temperatures. So meaning these liquids mix only at some proportions and become saturated at a certain concentration. Common example is a phenol and water. So if a small amount of phenol is added to water at room temperature, it will completely dissolve and thus form a one-phase system. Addition of more phenol will lead to a formation of a saturated solution, which will be observed as a single-phase system. Recall that in this system, it is actually composed of two phases, with one phase that is being formed as fast as it disappears. Further addition of phenol beyond saturation results in the formation of two phases, the extra amount no longer being dissolved. So it should be also noted that at equilibrium at each of these two layers are saturated solutions of one in the other. Now, the same changes will take place if addition is done in reverse order. So let's say water is also added to phenol. So water is partially soluble in phenol and will dissolve in phenol to a limited extent. So take note that a temperature here is of consideration for partially miscible liquids. So as mentioned, these liquids mix only at some proportions and they become saturated at a certain conditions. So if the temperature is increased, what is expected to happen is the solubility of one liquid in the other is being increased. So thus, if we have a higher temperature, a greater amount of phenol or water will therefore be needed to reach saturation. Now, the stages that is undergone that by the system as phenol is gradually added to water can be pictured or diagrammed as this. So we have unsaturated solutions first, thus we have one phase. Next is we will be forming a saturated solution in which we have two phases and a two-layered system in which we also have two phases. Now, what do you notice with the diagram of partially miscible liquids? So the diagram, it features a dome-shaped curve, so which corresponds to saturated solutions of one liquid to the other. Now, the region outside the dome, so this represents unsaturated solutions. While inside the dome, we have a system with two layers. So recall in our previous discussion that for two-phase system, each layer is a saturated solution of one liquid in the other. So for this two-layered system, the techniques we used previously like tie lines and lever rule can still be applied. So you know that lever rule is used to calculate the ratio of the amount or weight or in terms of number of moles of the two coexisting layers. Now, notice that in partially miscible liquids, we have what we call T sub C here. So T sub C refers to upper critical temperature. In some references, it's called upper consolute temperature. So this is the highest temperature at which separation occurs. Above this temperature, the two components are, we could say, they are fully miscible. Another condition that can occur for two partially miscible liquids to become completely miscible is the one in which we have a lower critical temperature. So an example of a pair of compounds that show this behavior is water and trimethylamine. So opposite of the previous graph, this shows a lower critical temperature or lower consolute temperature. Below this, they mix in all proportions, which they form two phases. So this curious behavior can be attributed to the formation of a weak complex, which decomposes at higher temperature. Now, there are also liquids, a number of systems which exhibit. So it has both maximum and minimum critical temperature. In this case, the phase diagram features a loop which encloses the two phase region. So the common example is nicotine and water. So in the case of nicotine in water, it has a lower critical temperature of 61 degrees Celsius, and it has an upper critical temperature of 210 degrees Celsius. Okay. Now, as I mentioned, we will also be considering Lever rule here. So recall that for two-phase system, so each layer is a saturated solution of one liquid in the other. So for these two-layered systems, the techniques used in the interpretation that we use in the liquid vapor equilibrium systems previously can be also applied. So let's say we have a partially miscible liquid system that has upper critical temperature. So let's say this is temperature. So by the way, most of the graphs here, we refer to temperature versus mole fraction since solubility is much dependent on temperature. So let's say this is a graph of temperature versus x sub b. So if we have x sub b here, at certain temperature here, so this is the, if you extend this to the line here, this is x sub b, B rich. And if we extend the line here at point A, and then this refers to the mole fraction x sub b, but A rich. So recall that tie lines connect the composition of the two layers in equilibrium with each other. So from this graph, the distance of point A here is x sub b minus x sub b A rich, and this L sub b. L sub b is equal to x sub b B rich minus x sub b. So recall Lever rule, so which is used to calculate the ratio of the weights or moles of the two coexisting layers. So thus, the ratio of mole of A over mole of B is equal to L sub B over L sub A. Okay? Now, let us try to analyze example number 1. So in example number 1, a mixture of 50 gram of hexane and 50 gram of nitrobenzene was prepared okay, at 290 Kelvin. Now, what the question is, what are the compositions of the phases and what proportions do they occur? And the next question is, to what temperature must the sample be heated to obtain a single phase? Now, in this case, the composition of the phases are given by the points, where a tie line through the point representing the temperature and overall composition of the system intersects at the phase boundary. So their proportions are given by the Lever rule. Okay, so if we denote hexane H as and then nitrobenzene N, so here we have X sub N as 0.41 at 290 Kelvin. So if we will be considering N alpha, this is the distance from L beta, or from the previous example, we from the previous equation we had earlier, it's L sub B. So L sub B, so which is if we extend this, so we have 0.83 minus 0.41. And N beta here is N beta, the ratio of N alpha over N beta is equal to L beta over L alpha. L alpha is equal to 0.41. So if we extend this to this line and then project this to X hexane rich, so 0.41 minus 0.35. So the answer is 7. So what does it mean? So this means that there's about 7 times more nitrobenzene rich phase than the hexane rich phase. And then heating the sample up to 292 Kelvin takes it into a single phase region. So that's how we use Lever rule to interpret composition in weights in a given partially miscible liquid. Okay, so again, this type of curve has upper critical solution temperature, so which means the upper critical temperature is the highest temperature at which phase separation occurs. So above this temperature, the two components are, we could say they are fully miscible. So this exists because the greater thermal motion will overcome any potential energy advantage in molecules of one type being close to one another. Now consider a pair of liquids that are partially miscible and form a low boiling azeotrope. So in this case, so as you can see in the graph, so it has a boiling, the system forms a minimum boiling mixture, okay? It exhibits a phase diagram similar to, so it combination of a non-ideal solution and partially miscible liquids. So for some cases, the boiling point of the azeotrope approaches the consolute temperature. And thus, what is happening here is the two curves merge. So resulting in a phase diagram similar to the one shown in the right. So if we will interpret this, so example, there's a phase diagram of a system in which liquids become fully miscible before they boil. So example, if we will distill a mixture at A1, okay? Now, so of course, temperature will be increased and leads to a vapor with composition B1, okay? And then when it condenses completely, it could condense to completely miscible solution at B2. Okay, so because this phase is liquid. And then phase separation occurs when the distillate Okay, this the distillate, the one we collected from the distillation, is cooled to a point in the two-phase region at B3. Okay, so another thing that we could say here, that this temperature composition diagram in which the upper critical temperature, so this is the upper critical temperature, so this is less than the boiling points at all compositions. So thus the mixture is forming a low boiling azeotrope. So what is the difference from this curve? So this figure is for the situation in which boiling occurs. So boiling happens first before complete miscibility. So this means that we don't have the upper um, critical solution temperature. So the boiling point of the azeotrope approaches the consolute temperature. So the two curves merge, which results in this phase diagram. So that's how we could picture different figures of partially miscible binary liquids. Now, let us go to immiscible liquids. So consider a mixture of components A and B. Of course, they are immiscible because they are mutually insoluble. So because of the absence of favorable interactions between the molecules of the two liquids. So A and B here do not interact. Okay, so it's a known fact that immiscible liquids are mutually insoluble, and they are depending much on the densities of the liquids. So how do we approach or analyze immiscible liquids? So in a mixture of two immiscible liquids, so remember that each will behave like a pure liquid, as though it were the only liquid present. So as I've mentioned, this is because of the absence of favorable interactions between the molecules of the two liquids. So therefore, addition of one liquid to another will not cause a modification in terms of the properties of either liquid. So since A and B do not interact, Rolle's law cannot be considered anymore. But of course, we could employ Dalton's laws because each liquid is behaving like a pure liquid. So the sum of um, the total pressure is equal to the sum of its vapor pressures. So this behavior is very useful in the purification of a water immiscible organic liquid, which has a boiling point and which decomposes upon boiling. So recall that this technique is known as steam distillation. So because in immiscible liquids, this is independent much of the composition, the partial pressure of the components in a mixture as the same as in the pure component. Okay, so each liquid will equilibrate with its vapor independent of the other liquid and exert a vapor pressure similar to the pure liquid. So remember that if we are considered interested with the composition of the vapor, so this is how our equation looks like. Okay, now take note that vapor pressure of the mixture is higher compared with pure components. So therefore, if the pressure of the vapor pressure of the mixture is much higher compared with pure components, what do we expect with its temperature? So the mixture will attain a pressure of 1 atmosphere at a lower temperature than pure liquids. So we could say that its normal boiling point, it's the reverse. It's much lower than that of pure component. So remember that the boiling point of the mixture will remain constant as long as the two immiscible liquids are present. So this behavior is used in the purification of water immiscible organic type of liquids in the case of steam distillation. Okay. Now, to continue this equation, so YA over YB is equal to PA asterisk over PB asterisk. So in terms of number of moles, NA over NB is equal to PA asterisk over PB asterisk. So in terms of weight, so the ratio of weight of A over weight of B is equal to the ratio of products of um, vapor pressure multiplied by molecular weight. So this equation gives the relative weights of each component in a vapor phase. So during distillation, the vapor is converted into distillate so that this equation can be used to determine the relative amounts of the components in a distillate during steam distillation. Okay. So as I mentioned, one of the applications is steam distillation. So in steam distillation, it allows the separation of heat-sensitive materials that must be immiscible with water, like oils or non-polar organic liquids at much lower temperature. So let's say less than 100 degrees. Of course, because we are considering steam or introducing steam and the distillation. So what is happening here is a steam is blown through the mixture. So let's have an example like water and phenylamine. So that turn into vapor. So thus the vapor can be condensed and collected. So how do we generate the steam here? The steam can be generated by heating the water in another flask or like a similar flask. So as the hot steam passes through the mixture, it condenses and releases heat. So this will be enough to boil the mixture of water and phenylamine. So let's say 98 degrees Celsius, so lower than 100, provided that the volume is not much. It's not much, no? But for large volume, it's better to heat the flask as well as to avoid having to condense too much steam and increase the boiling of liquid of the flask in the flask too much. Okay, so thus what is happening with the condensed vapor? The condensed vapor will consist both of water and phenylamine. If they were truly immiscible, they would form two layers. And then you could separate it by a separating funnel. So those are some other applications of steam distillation. Example, in the case of natural products, to extract eucalyptus oil from eucalyptus, citrus oils from lemons or orange peel, and to extract oils that is being used in perfume from various plant materials. Okay, let's continue on the condensed phase equilibrium. So in the succeeding sections, the vapor pressure will be disregarded and will be considered as not being involved in the phase equilibrium. So the total pressure here will be set at such a value that the components will not exist as a vapor. So under these conditions, the components will occur as solids and liquids. And these systems can be described as condensed systems. So recall our phase rule, F is equal to C minus P plus 1 here. And then for the two component system, so we have F is equal to 3 minus P. So in the condensed phase equilibrium, these systems are not affected significantly by small changes in pressure, so that the pressure here can be assumed to be constant. Now, for condensed phase equilibrium, um, we have complete miscibility in the liquid phase, and we have different cases. So case one is only pure components crystallized from the solution. So meaning we have no reactions here. And in the case two, there is a chemical reaction occurring between two components. And under chemical reactions, we have eutectic reaction, which forms a congruently melting compound, and a peritectic reaction, forming an incongruently melting compound. So the equilibrium between a solid and a liquid in a binary mixture can be viewed from the point of the two common but distinct processes. So it can be solidification or freezing of a liquid and saturation of a solution. So the solidification of a liquid is of course brought about by lowering of the temperature of the system. And the phase change can be monitored by what we call thermal analysis method. So thermal analysis method involves the study of the rate of cooling of liquid mixtures. So in the diagram, the slope of the temperature time curves could indicate the occurrence of phase transition in the system. Now, normally, in solid liquid equilibrium, in the degrees of temperature, the rate of temperature drop is not uniform. So if we will try to compare the cooling curves of a pure substance versus mixture, so uh, the in the case of pure substance, there is a sudden break here in the cooling, and the subsequent absence or subsequent appearance rather of a plateau in the cooling curve. So for a mixture, there is a gradual change in the slope before here at this point, before the curve flattens. So these behaviors are presented here. So the appearance of a solid upon saturation is a result of a limited solubility of a solid in a liquid at a given temperature. So we all know that solubility of solid is decreases as temperature is being decreased. Okay. So that occurrence of a saturation is dependent on the temperature of the system. So class, this is the basis of what we call the saturation method in the study of solid-liquid equilibrium. So this method involves the determination of the temperature at which a mixture of a given concentration becomes saturated. Okay? Now let us try to understand solid systems case one. So this is how the graph looks like. So some systems form a liquid mixture which exhibit the cooling behavior in similar to pure substance. So this mixture are known as what we call eutectic mixture. So recall that in pure substance, there's a sudden break in the cooling curve. So what are eutectic mixtures? Eutectic mixtures is made up of fine crystals that are intimately mixed with each other, thus causing it to behave like a pure solid. So it should be pointed out that this mixture is composed of two solid phases, okay? And it exhibits the following properties. So number one is solidification of the melt is initiated and completed at the same temperature. So this indicates that there's no change in composition that takes place in solid and liquid phases. And the solid phase and liquid phase are in equilibrium with each other. So at this point, and they have the same composition. So another thing that we will remember is this is the lowest melting um, mixture formed by the system. So from the Greek word eutectos, which means easily melted. Okay. Now let us try to analyze further the phase diagram of a system in which there is only one eutectic mixture that is being formed. Okay. So points D and F here. So points D and F, so it refers to the freezing or melting points of pure A and B. So recall that temperature versus A, so this refers to pure B and this refers to pure A. Now, what could we say about curves DE and Fe? So this gives the freezing point of the mixtures, okay, which contains A and B. So note that the freezing point is lower than the pure substance, okay, and the area above the curves here, so this refers to unsaturated solutions, or what we call the melt. So in here, the system consists of only one phase. So a liquid phase, and it has 2 degrees of freedom. Okay. So below these curves, okay, below the unsaturated solution, we have what we call saturated solution and a pure solid that separates from the solution at a particular temperature. So in here, we have 2 phases. So thus the degree of freedom is 1. Now to analyze this, a tie line can be drawn for a particular temperature to determine the composition of the 2 phases. So example, if we will be considering the tie line, KL, so this indicates the equilibrium mixture of pure B and saturated solution L. Okay, what about the tie line MN? So the tie line MN indicates an equilibrium mixture of A and saturated solution M. Okay, so of course, point E here is the eutectic mixture. Okay, so there are 3 phases here in the system. So solid A, solid B, and solution C. So that the degree of freedom would be equal to 0. So in the eutectic mixture, the system is invariant and can exist only at one unique temperature and a fixed concentration C. Okay. Below the eutectic mixture temperature, solid that will crystallize out in the system. So this is called the eutectic mixture. So in this, on the right side, we have solid plus eutectic mixture, and the left side we have in terms of solid B plus the eutectic mixture. So in this type of diagram, the lever rule can still be applied in this case. So let's say we are going to example, weight of ratio of solid or weight of A over weight of solution. So we can still employ tie line. So that's how we picture the phase diagram if we have one eutectic mixture. Okay. So to further understand here, so in terms of A1 to A2, the system enters the 2-phase region labeled as liquid plus B. The pure solid B begins to come out, and the remaining liquid, of course, becomes richer in A. So A2 to A3, more of the solid B forms, and A3 to A4, at the end of this step, there is less liquid than at A3. Okay. So this liquid now freezes to give a two-phase system of pure B and pure A. Now, let us try to understand the second case. So this one is a eutectic reaction which forms a congruent melting compound which melts without decomposition. So this is stable up to its melting point, yielding a liquid with the same composition as the liquid. So remember, in a compound formation, two types of compounds could be formed. So this one, this is the first type, a congruent melting compound which melts without composition. So as I mentioned, this is stable up to its melting point, which yields a liquid with the same composition as the solid. So the formation of a congruent melting compound can be recognized in the phase diagram through the occurrence of what we call maximum. So the melting point of this compound is a maximum in the curve. So take note also that a congruent melting compound exhibits a cooling behavior similar to the pure substance. That is, its melting begins and is completed at the same temperature. Okay, so if we will analyze the points here, okay, the congruent melting compound is represented by point M, okay, then points L and N here, okay, L and N, this could represent as the eutectic mixtures. So eutectic L here is made up of crystals of B and AB, and eutectic N is composed of crystals A and AB. Now the curves KL, so this contains saturated solution of B. Okay, curve NO here contains saturated solution of A because this is A-rich. And then curve LM and MN are saturated solutions of A and B. So the area above the curves, so above the high temperature, it corresponds to unsaturated solutions or melt. So below the curve, so below KL, so this composes of B and saturated solution of B. So below curve LM. So this refers to AB and saturated solution of AB. And below curve MN. So this is AB solid and a saturated solution of AB. So below curve NO, this is solid A and saturated solution of A. So again, to understand it more, so below curve L, so saturated solution of B only and solid B. NO refers to a solid and saturated solution of A. At this point, below the melting, below the high temperature, LM is and MN consists of saturated solution of AB with solid AB. Okay. So the composition of the two-phase system, so if we have a two-phase system, this could also be deduced through use of tie line drawn at given temperature. So the Lever rule enables the calculation of the relative amounts in each phase. So I've just shown a graph that has that can form only one congruent melting compound. But in reality, there are systems that can form several. So we have like a lot of this, several congruent melting compound. Okay. So the last type is the peritectic reaction. So thus it forms an incongruent melting compound. So the incongruent melting compound decomposes on melting. So it yields a new solid and a liquid phase with a composition different from that of solid phase. So the decomposition reaction is called a phase reaction or transition, more commonly known as the peritectic reaction. So the reaction occurs at a temperature known as the peritectic or the transition temperature. So the temperature remains constant as long as all phases involved in the reaction are present. When one of the phases disappears, the temperature will change. So the typical phase diagram for a system, which involves a non-congruent melting compound, is shown below. Okay. So point P here, okay, is the peritectic point. Okay. So recognize that the solution P here is in equilibrium with two solids A and AB. So which means at peritectic point, we have three phases. So thus the degree of freedom is equal to 0. So the non-congruent melting compound can exist as a solid only below the peritectic temperature. Above this temperature, the solid phase will consist of the decomposition product, or what we call, let's say, decomposition product of the peritectic reaction. So curve KL here corresponds to saturated solutions of B. Okay, curve LP contains saturated solutions of A and B. Okay, until it reached the peritectic point. And then curve PM contains saturated solutions of A. So the area under these curves represents a two-phase system which consists of what? Saturated solution and a solid solute. So point L here is the eutectic mixture. So which is made up of crystals B and ABS. Now for binary solid systems, remember that you need to categorize it by reactions, if it has reaction or none, and then you will determine how many phases are present and what are the components present at each point. So to summarize a discussion on binary systems, so we discuss miscible liquids, ideal and non-ideal. We also discuss partially miscible liquids. We also discuss immiscible liquids and condensed phase, or common examples of solid liquid systems.